Hello everyone. Today I want to talk about the modeling of stress-strain relationship of advanced high-strength cold-form steel at evaluated temperature. Advanced high-strength steel are developed with advances in material science, and they have brought great improvement in terms of material properties that may be used in structural engineering in a very near future. And here we have a figure showing the relationship between their tensile strengths and their elongation for both conventional steels and HSS, where we can see the advancement of their HSS compared with the conventional steel. And to achieve this promising future, we have launched a large-scale project to better understand their material properties and structure performance. So for these grades, we try to understand different perspectives of it, including the material properties, member behaviors, and also the structure behavior at a structure level. Material properties will be the prerequisite for us to understand its behavior, and this will include different scenarios, which include the evaluated temperature scenario. So we conducted a series of tensile coupon tests following different test methods to investigate the material properties at evaluated temperature. And then we use this database for the stress-strain behavior at evaluated temperature modeling, which could be a very important part for the advanced nonlinear numerical simulation for structure under fire. So for the evaluated temperature scenario, we have two different test protocols. One is the steady state test and one is transient state test. In this study, we use the steady state test, which can output the stress-strain curve more directly and straightforward. Here is a graph to briefly show the fundamental procedures of the test. Each specimen was firstly placed in the furnace, and the temperature in the furnace is raised to the target temperature, and we will wait that the evaluated temperature we selected is evenly distributed inside the specimen, and this is monitored by pairs of thermocouples that directly contact with their specimens. Then we will conduct our tensile test until the specimen fracture. The output is the applied load and the strain measured from the extensometer. The engineering stress can be easily calculated by the applied load over the cross-section area we measured before the test. And here is one of the examples for the result, showing the relationship between stress and strain for one steel at different evaluated temperature. So for the test metrics, we have 5 different materials, which including 2 dual-phase steel, 2 metal-synthetic steels, and also we found one high-strength low-alloy steel sheet showing pretty similar stress-strain behavior with our HSS. So we will also include an HSLA with a nominal yield stress of 700, and we also can see the thickness of each steel sheet. And for the target temperature, we test at ambient and also 200 to 700 with an increment of 100 for each case. This is the test result for the 2 DP, and these are the stress-strain relationship for the 2 MS at different temperatures. And the last one is for the HSLA. We notice that all curves show some unique characteristic. One is the all-rounded curve shape, and we do not see any clear or distinct yield point or yield plateau, but a gradual yielding process. And for each of their steel, from ambient to around 500 or 400 degrees, we see the curves generally have a very large degree of curvature than their counterpart at higher temperature cases. This phenomenon is particularly obvious for the DP and HSLA, while less obvious for the MS steel. So we have got the stress strain curves from the test. Then we will use this database to propose a simulation for this relationship at different evaluated temperature. First of all, we try to use the existing models from literature to fit our HSS stress strain curve database at evaluated temperature. And from the literature, there are two types of models that are pretty popular. One is a one-stage beta model, and the other one is a two-stage model. Both of them are based on the Rambert-Osgood equation, and unfortunately, none of them can provide accurate fit for our HSS database. Here we show an example at the bottom left, where the 200-degree cases, both models cannot provide accurate fit, and for the 500-degree cases, the two-stage model can provide an accurate fit, while the one-stage beta model still cannot provide an accurate fit. And these inaccuracies are caused from the unique characteristic of our HSS stress strain curves. And we summarize all the causes and analysis the rationale behind it in this paper. And here we want to emphasize 2 points of it. One is it has a very long yielding plateau at high strength range. For example, from the point with their stress equal to 99% of the ultimate strength to the ultimate strength, we only see a 1% of stress increment, but we see a 40 to more than 100% of increment for the strain, which indicate this long tail part is generally a horizontal line parallel to the strain axis with a very small slope. And the other characteristic is around the yield point, where we see a very rounded strain hardening behavior around that point. And one indicator is the ratio between the ultimate strength and the yield strength, which can be up to 1.6 for some cases, and most of the ratio is above 1.5. Based on the analysis on the causes for the fitting inaccuracy using existing models, we try to make some updates to provide a more accurate fit. And so the model we provide is also based on the Rambert-Osgood equation, and it is a two-stage plus linear model. We can see a figure showing bottom left, showing how we divide each part. So for the first stage is from the origin to the P-proof stress, and the second stage is from the P-proof stress to the equivalent ultimate point, which has a stress value equal to 99% of the ultimate strength, and the final linear part is between the equivalent ultimate point and the ultimate point, and is simply depicted by a straight line. For the p-value, it will not constantly be 0.2% as the conventional practice. We iterate different p-values from traditional 0.2% to 3% with their increment only 1.1% for each curve of each steel at each evaluated temperature we tested using error minimization method, and we find the optimal p values with the largest R square for each steel at each evaluated temperature. And here is a summary of the p-value we recommended for different steels. From the table, we see a very obvious decreasing trend of p-value when steel grade increases. And also for temperature cases at or higher than 500 degrees, the traditional 0.2% proof stress is accurate enough. Here are the relationship between the fit using our proposed two-stage plus linear model with the test stress strain curves for different steel at each evaluated temperature. This slide shows the two DP steel and the HSLA steel. This slide shows the MS-1030 and MS-1200. And for all the test curve we have, the model can provide an accurate fit with the R-square larger than 99.5% for any of the test curve. And we finally come to our concluding remarks. First of all, we introduced our experimental study, which is trying to understand the HSS material property behavior at evaluated temperature, and the major output or result from the test is the engineering stress strain curve of the HSS at evaluated temperature, and the result is used as the database for our modeling study. And for the modeling study, first of all, we try to use the existing stress strain models for cold form steel and stainless steel at evaluated temperature, and we recalibrate all these models to fit our HSS database. Unfortunately, these existing models cannot provide accurate fit for our database. Based on the causes of the inaccuracy for the existing models, we developed a new two-stage plus linear stress strain model, and compared with previous or existing models, it does not increase the complexity of the model, and the new model is able to provide accurate fit for the evaluated temperature HSS database with the minimum R-squared larger than 0.995 for each case. And yeah, that's all I have for today. Thank you for your attention, and I'm glad to take any question or comment. Thank you.